Hello everyone, I'm Xianghao Zhan from Department of Bioengineering at Stanford University. Today is my great pleasure to present our work for this year's CAMDA challenge, and the work is entitled The AI-based Filter of Drug-Induced Liver Injury Publications with Natural Language Processing and Conformal Prediction. Drug-induced liver injury are also referred to as the DILI, the abbreviated as DILI. They're referring this kind of the unexpected adverse reaction to drugs, because DILI can sometimes lead to acute liver failure and even death. And therefore, it has become a main killer of the novel drug candidates for the drug discovery. Therefore, as researchers in this field, we always try to think of better prediction methods or diagnosis of drug-induced liver injury. But there is a huge challenge in this task because information related to drug-induced liver injury or DILI is mainly stored in the literature corpus and therefore require lots of manual work of human screening. But recently, with the development of natural language processing, there is a possibility for us, an opportunity for us to develop the NLP tools, the natural language processing tools, to rapidly classify the drug-induced liver injury-related papers for potential faster processing of the potential drug candidates with high accuracy. So in this study and in this challenge, we are going to use the data set with the PubMed papers with the DILI related, which also we refer to this as the positive cases, and also the unrelated papers as negatives. And these data sets has been curated by FDA experts, and what we need to do is build classifiers based on these natural language processing techniques and try to predict whether a publication is related to DILI or not based on its title and abstract. For the positive cases, there was about 14,000 cases, and only 50% was released for the more development stage. And for the negative cases, there were also around 14,000 cases, and only 50% were released for the more development stage. And the format of the data includes the CSV files with title and or abstract. Not all cases, not all samples are with both title and abstract. And here is just a brief snapshot of the data format. And with this data set, with this release data set, we can develop models. And finally, the performances will be tested on the holdout test or validation sets. There are 7 of them and 3 different test sets, and including different number of abstracts. And the test set 1 is a balanced data set with the same number of positive and negative cases. And for the test set 2 and test set 3, the data set is assumed to be imbalanced according to the CAMDA challenge. And for the 4 validation sets, in addition to the 3 validation sets that resembles the test set, there is one additional validation set, V4, validation set 4, that includes 14,000 expert summaries of the research. So there is we hypothesis that there could be some data distribution drift, and this data set can be used to test the model's performance on different types of literature, on different type of text, and data distribution drift. And before we get started with the modeling process, the first thing we need to do is to process the data. And here, we firstly partition the entire dataset into 80% training dataset and 20% internal validation dataset. Here, the internal validation dataset is used by us to tune the hyperparameters and choose the model. And here, after we finish the dataset partition, we perform the lower casing of the text and remove the punctuation, numeric URLs, and also remove the stop words. And additionally, we also perform the word stemming by reducing the words to their word stems. And we regard the stemming as the hyperparameter that is going to be tuned on the performance on the internal validation data. And here, we perform all the modeling with Python and all the pre-processing with GenSim library. And the next step will be text vectorization to vectorize the text to be embeddings, to be numerical vectors that we could use to build learning, machine learning, deep learning models. And here we use different types of vectorization approaches. First one is the simplest one, the simplest type of word-based text vectorization. The first one is the bag of word. It simply counts the frequency of the word appeared in a document and use that as the feature. And the second one is the TF-IDF model, which is a normalized version of the bag of word, and not only take into consideration the word frequency in a particular document, but also the number of documents that contain this word. So the TF-IDF can further emphasize the words, the rare words or rare terms that appear in a particular document. And the third one is the word-to-vec model. And here we use two pre-trained biomedical word-to-vec model trained by different researchers, and we refer to them as the word-to-vec 1 and word-to-vec 2. And the second type of vectorization approach we use was a language modeling-based vectorization. Here we use a pre-trained bio-Sim2Vec model that has been trained on the PubMed and Mimic3 dataset, which embed the text into a vector with a dimensionality of 700. And finally, to compare the simpler model, the vectorization models with the nowadays very hard large pre-trained language models, we also performed the analysis of the modeling on the BioBERT, which is the biomedical bidirectional encoder representations from transformers. And here we use the BioBERT-based version 1.2 as a comparison, that is try to see whether the simpler model or more complex model, which one will perform better. And with these vectorization approaches, what we're going to do is the modeling process, and what we have done are these 5 different types of experiments. Firstly, we train different classification models based on the separate vectorization models. And secondly, we performed ensemble learning training model, ensemble learner training. So in this case, we ensemble different types of vectorization approaches and use a logistic regression on the top of the predicted probability to ensemble the decisions made by different vectorizers. And the third step will be the model robustness test. We'll perform the bootstrapping on the training dataset and analyze the model performance and model robustness across different parallel experiments. And with this experiment, we're also able to show which model is superior to others with statistical significance. And the fourth experiment was a model interpretation, because we are generally using the simpler word vectorization approaches. So our model maintains the interpretability. So we could interpret the model results and show the important words that directly lead to the positive prediction or negative prediction. And the last experiment we are going to introduce in today's presentation will be the reliability quantification with conformal prediction. Before we moving forward here, I would like to introduce 2 general model development pipelines in this study. First one is the non-ensemble learning models, which is also shown in the first one, the separate model training. So for this type of model training pipeline, we directly use 80% of the training data to train a classifier and use the 20% internal validation data to tune the hyperparameters. And for the ensemble learning pipeline, we further partition the training dataset. So after the dataset partitioning, there was 60% of the total data that are going to be used to train the separate learners with different vectorization approaches. And then the 20% of the total data will be used to train the meta learner that will aggregate the predicted probabilities made by the separate learners. And finally, the internal validation data, the 20% data, will be used to tune the hyperparameters of the meta learner. And here, we're going to show you the results of the separate models first. For the separate models, firstly, we show the performance on our internal validation data set. Here we show the results in table 1. And this result shows that generally when compared with other approaches, the TF-IDF outperform the other different separate learners. And as we look into the exact predictions the models made and errors they made, we look at the false positive and false negative made by these models, we could see that although there is a huge part, the models errors overlap, different models have their different characteristics. So different models have their great diversity. So this motivates us to ensemble different type of separate learners so that we could make use of their different judgment and probably lead to better performance. And meanwhile, to further quantify the diversity, we have also calculated the pairwise kappa values. So we can see that the closer to 1.0, the less diversity in each pairwise comparison. So generally, we could see that for different separate learners, their predictions bear high diversities, and this diversity could be leveraged in the ensemble learning protocol. To develop the ensemble learning protocols, firstly, we dropped the bag of words model because the TF-IDF model generally outperforms the bag of word models, and they are pretty similar as word-based vectorization approach. The TF-IDF with further normalization and its performance is better than bag of words. And to reduce the complexity, we directly drop the bag of word model. And here we ensembled 12 different types of models for 4 vectorizers and different model weights. Here, we'd like to mention that the model weights are decided because in the real-world applications, the negative samples should be far more than the positive samples. So by adding the different weights to enable the model to attend to the positive cases, the models may be able to focus more on the positive cases in the model and may be better in predicting the real-world literature and publications. And here we tune the L2 penalty of these separate learners based on the 5-fold cross-validation on the 60% data that is used to train the separate learners. And here shows the results after we included the ensemble learning approach. And with this result, we can see that generally the ensemble learning models perform similarly to the TF-IDF model as the best separate learner. And with the metrics on accuracy, PRC, and F1 score the same as TF-IDF, and the AURC similar to a little bit smaller, lower than the TF-IDF model. And we have also visualized the receiver operating calculus curves and precision recall curves, and all the models seem to perform well on the internal validation data set. But this is just one-time experiment or single experiment when we train the data on the data set we partitioned. This does not show the model's performance robustness over different data set partition. So next step, we perform the model robustness test by doing the parallel experiment with bootstrapping. So we simply bootstrap the training data used to train the different separate learners, or the 60% training data to train the separate learners for the ensemble learning models. And we perform this bootstrapping with experiments with 100 times or 100 repeats. And here we show the result in the mean as well as the 95% confidence interval to show the model performance variation across different dataset partition. And here, after we perform these parallel experiments, we could see that the ensemble learning models is generally the best performing models, and the TF-IDF models their performance are similar to the ensemble learning models, but statistically significantly worse than the ensemble learning models, but the margin is not very large. Here we can see that the general takeaway from this table is that the ensemble learning model and the TF-IDF model significantly better than other models, but the simpler TF-IDF models may take much shorter computational time, as we can see that vectorization takes only less than 2 seconds, and the modeling time is also smaller than 1 second. But for the ensemble learning model, because we are ensembling different separate learners, we have to load all the word-to-vec models with a pre-trained model loading time. The word-to-vec model 2, also we have to load all these models for the ensemble learning model, so it is taking longer time in the modeling time. So with similar performance, the TF-IDF may be a simpler model, and yeah, it may be quicker and maybe faster to train and to be used. And the last model we have compared with all the different models we developed is the BioBERT model. They are also performing well, but generally performing worse when compared with the other models. And we are going to show them visually with the plots of the AURC and AUPRC. Here we show the general relationship of these models with their performance variation across this 100 different bootstrapping experiments. You can see that the ensemble learning model and TF-IDF model are taking a lead in both the AURC and AUPRC. And generally, the word-to-vec models and pre-trained BioBERT model are lagging behind. But overall, the AURC and AUPRC are pretty high for all of these models. And we have also shown the result accuracy and F1 score. Here we still see that the ensemble learning model is performing the best, and TF-IDF is following the ensemble learning models, and their performance are quite similar. But when we test our models on the holdout test dataset, here comes result. It turned out to be that the simpler TF-IDF model works even better on the holdout test and validation dataset. So we have got the accuracy is pretty high for both the TF-IDF and ensemble learning model, but generally the F1 score, which is a score that different models use, this contest used to score the context score. Yeah, so and also the ranking, and it's based on F1 score. So generally, the TF-IDF model is performing slightly better than the ensemble learning models. So this may indicate that for the holdout test data set where we have the abstracts that really enable us to pick more into the publications, the TF-IDF model is performing well on this kind of data, as the feature dimensionality is higher, and once more information is given to this model, it can perform slightly better than the ensemble learning models. And we hypothesize that if the holdout test data set are only with the titles, not the abstract, the more general model, the ensemble learning model that benefit from the pre-trained word-to-vec model, pre-trained center-vec model, that may be performing better. But here with the abstracts, that with more information given by the long abstract, the high dimensionality of the feature space of the TF-IDF may have enabled the TF-IDF to perform better than the ensemble learning model. And the major advantage of the TF-IDF model is not only its simplicity, but also its interpretability. So here, with the TF-IDF model, we perform the logistic regression, and we also bootstrapped on the logistic regression for 1,000 times and calculate the regression coefficient in the logistic regression to see how positive these correlations are. The more positive the coefficients are, the more the words are related to the positive predictions, and the more negative just showing that the words are more related to the negative predictions of the daily publications or unrelated publications. And here we ranked the coefficient by their mean. You could see that on the positive side, the top 10 words include the words such as safety, hepatotox, liver, hepatotoxic, efficacy, and placebo, for instance. I think these words are really making sense because they are related. They are very much related to the drug-reduced liver injury researchers, such as there are some word stems such as hepatotox, hepat, and liver. And on the other end of these important word analysis, there comes the words such as rat, vaccine, express, cell, differ, procedure, radiate. And these seem to be the word stems that are not related to drug-induced liver injury, but more related to other fields of biomedical researches. So we are thinking that this model, the TF-IDIF model, which is not only simple, but also interpretable, and this can really enable the clinicians and also the users of the model to fully understand how this TF-IDIF model works. And so there could be higher fidelity in using this kind of model. And additionally, we have also interpreted the contribution by different separate learners in the ensemble learning models. We have also performed the bootstrapping on the meta-learner training data, and we have shown the coefficient in the logistic regression of the meta-learner, and which shows that firstly, all the coefficients are positive, which indicate that all these different separate learners are contributing, but the contributions are coming more from the first three TF-IDF model and the last three center-back models, which generally shows that these two types of models are contributing more to the ensemble learning models as our model interpretation. And the last experiment we have done is reliability quantification. And the motivation for us to do this is to quantify the prediction uncertainty that could enable us to better detect the hard cases and avoid missing the drug-induced liver injury publications. And because generally with this kind of tool to filter the drug-induced liver injury publications, we really do not want to miss any DLE-related publications, because we want the researchers in the drug discovery, for instance, to have a look to at least have a hint of some news some information in the drug-induced liver injury publications. So that's the reason why we want to make a kind of failure protection mechanism with the uncertainty quantification. And here we use the approach of conformal prediction. So we use it to quantify the uncertainty by the conformity of a particular combination of feature and label. So this algorithm, which was developed by Vladimir Vogt in 2005, and nowadays there have been multiple different new algorithms derived from the conformal prediction. So here we use the conformal prediction based on the predicted probability. We firstly convert the predicted probability into the non-conformity measurement for each feature label combination, and the non-conformity measurement for particular sample is given by alpha I for a particular training example. And here we leverage the predicted probability given xi and what the conditional probability of y hat of y, and also because this is a binary classification problems, we can simplify this conversion equation into this one. So for if the feature label combination involves the negative label, then the alpha I directly equals to the predicted probability for the positive case. And if the alpha I, if the non-conformity measurement is calculated for the feature label combination with the positive example, it could be simplified by the 1 minus the positive prediction probability. And this is just derived from the first equation. And for more details, please you can also refer to our publication here. And at the inference stage, when we are looking at a new prediction with a potential label, and here we just need to look at the statistical percentile of the non-conformity measurement within the training data distribution. So we convert the the non-conformity measurement into a p-value, and this p-value could quantify the reliability of a particular prediction with the label being y. And here, the main takeaway of this algorithm is that the output of this conformal prediction is the credibility, that is the reliability of the most likely label. Because in real world scenarios, we do not know the ground truth, because not like our validation data set, we know the ground truth label is negative or positive, but in real world cases, our application we only know the prediction made by the model, but we do not know the ground truth. But meanwhile, we could compute the prediction credibility based on this framework. So we can leverage the prediction credibility to assist our judgment or assist our decision-making process on the predictions. So next, what we need to do is to analyze, firstly, how does the credibility reflect the model prediction accuracy? And second one, if we filter the prediction based on credibility, can we get predictions that are more likely to be correct? So here we also perform the analysis as listed before, and now we perform the bootstrapping. And in some ensemble learning models, here comes the result. For all the correct predictions made by the model, we could see that the mean credibility of these predictions are pretty high. But for the wrong predictions, for the false negative predictions and for the false positive predictions, the mean credibility over the 100 experiments is pretty low. So this generally indicate that the higher credibility may be associated with higher likelihood of being correct. And in the second graph, we performed analysis by filtering the predictions based on different threshold on credibility. Here, we look at the predictions that are with different level of credibility. And we could see that for the models or for the predictions with higher credibility, the accuracy are increasing. So that generally means that if we could set up a credibility threshold in the prediction, for instance, for the credibility being larger than 0.7, we believe the predictions automatically made by the model. But for these predictions that are with lower credibility, probably these predictions may not be that accurate. So probably we have to check them by ourselves. And with this reliability quantification, we also performed some example analysis. Here we showed 4 example cases, and the first 2 are predicted correctly. So we can see that for these 2 correct predictions, the credibility are high. And for the 2 wrong predictions, the credibility are pretty low. And here for the first example, we could see that there comes the word hepatitis. Yeah, but this title indicate that actually the model may not be directly related to the drug-induced liver injury, but the model may have detected the word hepatitis. So that means that the model to be predicting the positive cases. But the credibility is pretty low. So we can leverage the credibility information to indicate the users, okay, so these predictions may not be reliable enough. Maybe we need a double check. And the second wrong prediction example here is also with low credibility. It includes the word such as the hyperammonemia. So the word hyperammonemia may not be directly associated with the word stem related to hepat or liver, but that indicates something related to liver function, liver dysfunction. So the models that may rely on particular detection of particular words or terms may not be working well on these some cases, but the credibility are also low. So we can leverage this credibility information. So to sum up, how should we react with the prediction credibility or leverage the reliability quantification results? And here we give the user 2 strategies. First one, if the credibility is pretty high for the predictions with high credibility, for instance, larger than 0.7, we can accept the model prediction. But for the not that reliable prediction, for instance, with credibility smaller than 0.7 or smaller than 0.6, probably we suggest the readers or users to check the publication manually to avoid missing daily related paper. So with this credibility mechanism, the user could more confidently use this daily filter model so that we can enable the model to miss fewer false negative publications. And to sum up, this study leveraged the NLP technologies, the text vectorization technologies to develop a prediction model for drug-induced liver injury. and it could be applied in fast and reliably filtering of the drug-induced liver injury literature without time-consuming manual work. And our models that have developed in this study have some specific advantages, such as the model simplicity, the model interpretability, because the model are based on word vectorizations, and they are pretty simple, pretty quick, and the computational time is pretty short. And meanwhile, with the reliability quantification with conformal prediction, it is more likely that the users with this system can avoid missing the DILI related publications, the false negative predictions. But there are still limitations. So far, we mainly use conventional NLP text vectorization approaches, and we also only tested the BioBERT as a large pre-trained language models. But there are still lots of more new and newer language pre-trained language models, such as Transformer XL or Roberta, so that could be trained and tested on these tasks and see whether they could perform even better. And finally, I'd like to acknowledge the great support from my collaborator Fanjing Wang from UCL, and also my great PI Olivier Givard from Stanford Biomedical Data Science. And that's all. Thank you very much for the privilege of your time.